Welcome to this lesson on electric field intensity due to an electric dipole. Today, we'll specifically focus on the field along the equatorial line of a dipole. First, let's understand what we mean by an electric dipole and its equatorial line. An electric dipole consists of two equal but opposite charges separated by a distance. In our setup, we'll place a positive charge plus Q at position A0 and a negative charge minus Q at position A0, whereas half the separation distance d. The equatorial line is the perpendicular bisector of the line connecting these two charges. We'll consider a point P on the y-axis at position 0, y. Now, let's calculate the distance from each charge to our point P. Looking at our setup, we can use the Pythagorean theorem to find this distance. For the positive charge, the distance is the square root of a squared plus y squared. Similarly, for the negative charge, it's also the square root of a squared plus y squared, since both charges are equidistant from point P. Let's calculate the electric field due to the positive charge. The electric field at point P due to the positive charge is given by Coulomb's law. It equals 1 over 4 pi epsilon naught times q over r squared times the unit vector r plus. In terms of components, this is 1 over 4 pi epsilon naught times q over r cubed times the vector from the positive charge to point P, which is negative I hat plus yj hat. Similarly, let's calculate the electric field due to the negative charge. The electric field at point P due to the negative charge is 1 over 4 pi epsilon naught times negative q over r squared times the unit vector r minus. In component form, this equals 1 over 4 pi epsilon naught times negative q over r cubed times the vector from the negative charge to point P, which is I hat plus yj hat. Now, let's find the total electric field by adding the contributions from both charges. The total electric field is the sum of E plus and E minus. When we add these two fields, something interesting happens. The y components cancel each other out due to symmetry. The x components, however, add up. After simplifying, we get E equals negative 1 over 4 pi epsilon naught times 2qa over r cubed times I hat. Let's now substitute at equals d over 2 to express the field in terms of the dipole separation d. We have E equals negative 1 over 4 pi epsilon naught times q times d over r cubed times I hat. Substituting the value of r, we get E equals negative 1 over 4 pi epsilon naught times q times d over the quantity y squared plus d over 2 squared, raised to the power 3 halves times I hat. It's more convenient to express this result in terms of the dipole moment P. The dipole moment is defined as P equals q times d times I hat, where I hat is the direction from negative to positive charge. Substituting this, our final result becomes E equals negative 1 over 4 pi epsilon naught times P over the quantity r squared plus d over 2 squared, raised to the power 3 halves, where we've replaced y with r for generality. For points far away from the dipole, where r is much greater than d, we can simplify this formula. In the far field approximation, when r is much greater than d, the term d over 2 squared becomes negligible compared to r squared. So our field simplifies to E equals negative 1 over 4 pi epsilon naught times P over r cubed. Note that the field points opposite to the dipole moment direction, and it falls off as 1 over r cubed, which is faster than the 1 over r squared dependence of a single point charge. Let's visualize how the electric field varies along the equatorial line. As we move farther away from the dipole, the field strength decreases rapidly due to the 1 over r cubed dependence. The field lines always point in the negative x direction, opposite to the dipole moment. In summary, the electric field due to a dipole on its equatorial line: 1. Points opposite to the dipole moment, 2. Falls off as 1 over r cubed in the far zone, and 3. Has a magnitude that depends on the dipole moment P, which is the product of charge and separation distance. And here's our final formula for the electric field on the equatorial line of a dipole. Remember that this field always points opposite to the dipole moment and decreases rapidly with distance.